All right, I'd really like to compliment the workshop organizers. What a great place to have a meeting. I mean, a cabin in the woods, basically. This is my style. Last week I was up in Marquette, Michigan for the Great Lakes and St. Lawrence Cities Initiative Conference. And so it was a whole bunch of mayors in suits who are actually really well informed about Great Lakes issues. But it was in Marquette, Michigan, so it's a little bit of a mix of UP and big cities. And so, you know, some people showed up in plaid, and there was a guy that showed up in a boat from Thunder Bay, Ontario, so there was a good mix. But they also only gave me 15 minutes to talk about anything and everything having to do with climate change in the Great Lakes, so the pressure was a little bit higher than it is here. So I like the casual setting. And speaking of casual, I'm wearing my Wisconsin Badgers hockey t-shirt because I was hoping to watch hockey last night, but the Bruins couldn't pull it off the other day just to extend the hockey season. And also because my introduction to limnology was actually in Wisconsin. So I unabashedly say go Bucky Badger. I know there's a few Wisconsinites in the audience. This is Sparkling Lake, and my background is primarily in atmospheric science. But after grad school, I got the opportunity to get out and put sensors on buoys on lakes and really start to look at the interactions between climate and water, primarily from a physical perspective. So that's sort of where I came from. What I do want to talk about today are those two projects that was in the title, the KLON project and the GLTC project. But I'll give a little bit of background. The talk's going to be probably 60-70% science and about 30-40% the networks and you know, building groups of people trying to answer similar questions. So I'll start by just talking about some of my main interests and research questions and the motivation for that, look at some of the methods that we're using in various field sites, and then talk specifically about these two large-scale projects, one focusing on Arctic lakes and the other one focusing on global lake temperature trends. So some of the main research questions I'm interested in are what are the impacts of climate variability and change on lake physics and hydrology. I'm not a biologist. I probably dabble a little bit in ecology, primarily what I pick up vicariously through other folks, but I am really interested in how what I'm studying impacts what you do. So if I can get feedback from you guys, that would be great as well. The things I study are mostly water temperature, evaporation rates, ice cover, and lake levels, which are, of course, all interrelated. Another main question that I'm interested in is how do large lakes and lake-rich landscapes interact with the regional climate? So I'm interested in the two-way coupling, not just the one-way interaction, not just impacts of climate on lakes, but when you have regions that have large lakes, such as the Great Lakes, or lake-rich landscapes, they, of course, influence the regional climate. So motivation, one of the motivations, of course, is lake level variations have wide-ranging impacts. I remember when I was at University of Wisconsin Center for Limnology, it seemed like there was always a debate about who had their favorite organism. And of course, I wasn't a biologist, but I said, you know what, my favorite organism is water. And if there's no water in the lake, you don't have any organisms. So there's, of course, water quality impacts, lake level impacts. Those, of course, impact commercial shipping on the Great Lakes, shoreline erosion, hydropower, tourism, recreational boating, and fishing on smaller lakes as well. So the impacts are wide-ranging. Lake evaporation is a key aspect of that, and that's sort of, I guess you could call it my bread and butter. That's one of the main processes I'm interested in. And it's partly because it does obviously impact the water balance. It takes water away from a system, but it also strongly impacts temperature because it's one of the strongest components of the energy balance. It's a strong cooling influence, so it impacts temperature and therefore stratification, chemistry, vertical mixing, and ultimately the lake ecology. So this is another picture of Sparkling Lake, and it's just sort of a schematic of the energy balance. I use energy and water balance techniques as well as other techniques to get at evaporation rates. This is the type of buoy that has been out on Sparkling Lake. This is sort of I don't know, second generation. There's a third and fourth generation out on Sparkling Lake now, but this was out there around 1989. And this kind of depicts the various inputs and outputs of energy to the lake system. So we have shortwave radiation or solar radiation coming from the sun. Some of that gets reflected. Long wave radiation, basically just the greenhouse effect, so just radiative heating from the sky coming down. A very small amount gets reflected, a very large amount gets emitted. And then there's two others that we're really interested in, the sensible heat flux, which is basically the temperature difference between air and water and the heat that takes away, and then evaporative heat flux, which is generally much stronger than H, and they're both largely wind driven, but also by temperature gradients. So you can add all these up, and if you take the net short wave, the net long wave, subtract off the cooling components, E and H generally tend to be cooling, you're then left with an imbalance. Well, it's just like balancing your checkbook. Anytime you have an imbalance, your balance goes up or goes down. In this case, the energy will go up or down in terms of the thermal heat content in the lake. All right, so to get at evaporation rates, sometimes what people do, and this is what the energy balance method does, you actually measure everything else and solve for evaporation as a residual. And that might sound fairly complicated and might sound like you're going to add up a lot of errors, but if you do the measurements pretty accurately, you get about 5 to 10% errors in the evaporation rates. There isn't like an evaporation gauge you can put out. There's pan evaporation gauges, but there's problems with relating that directly to evaporation from a lake. So this is an example of what you get when you do the energy balance method. This is a paper that Tim and I wrote with Carl Bowser back in 2005, and it just shows the evaporation rates on roughly 14-day running mean time scales from 1989 to 98. So a 10-year time series of evaporation rates from this lake. You can see that there's a lot of variation, right? So there's a lot of variations due to cold fronts coming through, wind events. So short-term fluctuations, there's seasonal fluctuations. Each year it tends to kind of maximize in late July when the water temperatures are the highest. And then there's also interannual variability. 98 was a high evaporation year, as was 1989. Mount Pinatubo erupted in 1991, cooled off much of North America in 92. That led to lower evaporation rates. And one of the interesting things we found from doing comparisons with the climatic data is we found that what drives evaporation is largely dependent on the time scale. So in short time scales, it's wind and humidity that drives evaporation, all these ups and downs. On seasonal time scales, it's temperature and radiation. And on interannual time scales, it's actually net radiation. So cloud cover becomes really important when you start to look at long-term variations in evaporation. So that's northern Wisconsin. Since then, I've been working on a few different field sites in Lake Superior, so a much larger lake, but in a similar climate. I've been out in Nebraska for 7 years, and we have a field site in semi-arid western Nebraska where we actually have saline lakes because they're groundwater fed. They don't run off, and so all their salts stay behind, and it's a very windy, dry environment, so there's high evaporation rates. And then, just for kicks, we throw in another extreme climate, and that's up in Barrow, Alaska, along the Arctic Ocean. So many different regional climates to see how does climate and climate change impacting these lakes in very different regions. I'll get back to Lake Superior in a moment, but this just quickly shows some of our monitoring equipment on an island that's just 20 kilometers due north of Marquette. This is known as an eddy covariance system, so it doesn't use the energy balance technique. It uses flux data, kind of like some of the towers we were hearing about from the NEON project, to measure evaporation and sensible heat flux and carbon dioxide fluxes over Lake Superior. This is a station out in semi-arid western Nebraska. It started out as a boat. It's a very alkaline lake, so it ate through the seals on the boat. The boat sank. We didn't really care. The lake's like this deep, so we just raised up the instruments. Became a very stable platform until a very large storm came through about a year ago and finally took the whole thing out. But we got three years of really good data. And very detailed energy balance measurements, including reflected solar radiation off the lake, which is influenced by not only the salts, but also the suspended solids, the algae in the lake. This is actually salt along the edge of the lake. That's not snow. And so the landscape I'll show you next is actually strikingly similar to western Nebraska. These are the Arctic thermokarst lakes. So thermokarst essentially basically means that you're getting expansion and contraction process from the freeze-thaw that goes on in the Arctic and the permafrost that's underlying it. So these thermokarst lakes, or thaw ponds as they're called, dominate much of this landscape, and it's flat, it's tundra, and so when we're flying over Alaska, It looks strikingly similar to Nebraska, and if you didn't know the substrate and the climate, you would think they were almost identical. Sometimes when I show the landscapes, I kind of joke by showing the different animals that live in the two regions, one being a caribou and one being a cow. And so if you can identify those two, you can identify the right region. But these are the types of systems we set up there. We have a data buoy on a lake in Barrow. We have land-based and water-based systems that we set up further south. And so this sort of is the lead into the KALON project, Circumarctic Lakes Observation Network. So what's the motivation to study Arctic lakes? So why the Arctic? Well, more than 25% of the world's lakes are actually in the Arctic. And it's also an area where climate change is occurring at a very rapid rate. On the other hand, systematic collection of key Arctic lake parameters is currently lacking. And so we recognized this and applied for funding through NSF's AON program. So just like there's EONs, there's the AON program, which is the Arctic Observing Network, and put in a proposal to begin monitoring lakes in the Arctic. And we chose the Arctic coastal plain of Alaska because roughly 40% of the Arctic coastal plain is covered by these thaw lakes or drained thaw lake basins. They go through a life cycle, and with all the freezing and thawing processes, many times these lakes will just drain catastrophically. There'll be a break and the lake is gone sometimes within hours or days. And then it takes a long, hundreds to thousands of years for that lake to reform and fill back up. So if you look at the landscape, it's just dotted with many of these existing lakes and former lakes. And this is another aerial shot kind of showing what it looks like. So a lot of overland flow, especially during the spring snowmelt. There's really nowhere for the water to go but to run off. It can't drain into the permafrost unless you're in a region of discontinuous permafrost. And this was the proposal we put together. We called it toward a Circumarctic Lakes Observation Network because we recognized that northern Alaska isn't circumarctic, but the idea being we already had some sites instrumented up there and we wanted to expand that network and then look toward working with Canadian and Russian colleagues down the road, northern Scandinavia, for example, to truly become circumarctic. So the short-term goal in the coming 4 years now is to expand and integrate the existing lake monitoring network that we have in Arctic Alaska, and then long-term goal being monitoring lakes throughout the Arctic. And this shows some of our sites. There's sort of two transects, a western transect and the eastern transect. And we have a number of different teams. I'll show the team members in a moment, but we generally fly into Barrow and go to points south of there, or go to Toolik and go points north up to Lake Teshikpuk, which is the third largest lake in Alaska and the largest lake on the Arctic coastal plain, and potentially the largest thermokarst lake in the world. So this is the KALON team led by our principal investigator, Ken Hinkle at the University of Cincinnati. He's got quite a team of investigators from UC. We have folks from University of Alaska Fairbanks, the USGS in Anchorage, Karen Fry from Clark University, myself, and Brittany Potter from University of Nebraska-Lincoln. Brittany graduated a year or so ago and stayed on to work for a while, but she's now taken a job in Pennsylvania. But she's contributed a lot of the images and data that I'll show here. So what kind of data are we collecting? Well, quite a range of data, water quality and biogeochemistry. That's mostly done through periodic sampling, but we do have auto samplers out collecting data throughout the wintertime, for example, sondes that are deployed under the ice in certain lakes. It's kind of a hierarchy of monitoring. So we have many lakes that are sampled with specific variables, but few variables, and then we have a few lakes that are sampled very intensively. We also have an indigenous knowledge component to the project, conducting elder interviews. There's really a rich history of native culture up there that have stories going back relating to these lakes. They use the lakes for subsistence fishing, and even the hunting of caribou is determined by where they have to go around these lakes. So there's a lot of interesting knowledge we can gain from the locals. Land-based weather stations, not only measuring things to do with the lakes, but also the sediment and permafrost. Shore-based and over-lake webcams, monitoring the conditions, including things like the ice breakup of the Mead River, and then floats and more sophisticated data buoys, monitoring ice on, ice off dates, ice thickness, surface reflectance, and some remotely sensed imagery as well. This is the buoy I showed earlier. It was actually a new Arctic Gleon site in Barrow, Alaska that we deployed last year in 2012, went out in July of 2012. The first Arctic site was, of course, Tulik, and so we'll be deploying that again in about a week or two, depending on when the ice comes off. Last year was actually a record early ice year, so hopefully I can beat it this year. We do quite a bit of wintertime data collection, as you can probably imagine, because the majority of our year up there is actually winter, about 9 months of it. So we'd be missing out a lot of the year if we didn't make measurements during the wintertime. This shows an example of a thermistor chain with 25 centimeter spacing, so we can monitor the ice temperature and ice thickness and the thaw process. These are our hobo sensors. I'll start to get into some of the sensor technology because I know that's an interest to some of you as well. So these are self-contained hobo loggers. They're very durable in the ice. We have a conductivity sensor down at the bottom. This is Brittany standing by one of the deployments. Sometimes we go out in April and core through the ice and put them in and then take them out in the summer and collect the data and redeploy them. This funky looking device I will describe in a moment. So here's an example of what some of the data looks like. This is the temperature at multiple depths from our primary study lake in Barrow, Alaska. It's known as Imaksoon Lake, which locally just means freshwater lake. That's where they used to get their drinking water. And this was the deployment, so you can see they immediately froze into the ice. This was deployed in mid-April. And all I'm looking at here is the deployment part until the thaw date. So even right here, the lake is not thawed. It actually looks like it is because it's above freezing. So this is down to 2 meters depth and up to 50 centimeters depth. And so obviously you kind of have to flip your intuition here a little bit because 50 centimeters is the shallowest one and that's the coldest one. And as you go down, it gets warmer until eventually you're no longer in ice. And once you get down to 2 meters, you're in water. So the ice thickness up there easily gets down to 1.8 meters in a given winter, very thick ice. And it looks like it's starting to warm up here, and it is, but that warm water is coming from the moats where it starts to thaw around the edge of the lake. And this is all actually still frozen. Not till it crosses about 3C do we actually have complete breakup and the ice gets blown to shore. And the reason this is going on here at 2 degrees Celsius, this is right around the summer solstice. So an immense amount of solar heating coming in on a lake that's got a giant ice cube in it. And I call it the margarita mix time of year because big chunks of ice moving around, trying to keep the sun from heating up the lake. They're fighting each other off and they're at about 2 degrees Celsius and can't get anywhere until the ice is gone, and then it shoots way up. And that shooting up process is right here. All right, so this blue period is the one I had just shown you, and that's what happens as soon as the ice is gone. Just shoots way up, and the solar radiation warms up the lake, and you might think, well, okay, now it's maxed out and there's still a lot of sunshine. 24 hours of daylight, why is it not continuing to warm up? Well, that's because those other components of the energy balance take over. Not only is the lake warmer and so it's emitting more long-wave radiation, but evaporation and sensible heat flux really kick in once the lake gets warmer than the air, which it generally is by this time of year. And it's actually quite windy up there. We get consistent 20 to 30 mile an hour winds out of the east-northeast about 90% of the time, which is actually great for keeping the mosquitoes away, so I don't complain about it too much. So that's what the temperature data looks like. And this instrument is what we use to measure surface albedo. I had a caption on there that apparently didn't show up, but it's supposed to say in rather curious ways. This is sort of the midnight sun. This is about 11 o'clock at night in April. So I always hear people saying how dark it is in Alaska, but even in April, we're starting to get more sun than most other folks. So we're out in snow machines at about 11 o'clock at night. There's Barrow off in the distance. And we took a tripod, tipped it upside down, drilled a hole in the ice, put a pressure logger at the bottom, and put 6 light sensors up at the top with some floats so that when the ice broke up, this thing would hopefully stay upright and move around and give us nice reflectance measurements of the ice. So what these measure are the incoming light from the sky and the reflected light from down below. And I'll explain in a moment why that's important. But albedo then is the ratio of the two. So it's the reflectivity. Ratio of the amount reflected divided by the amount coming down, and you get a percentage. Now, as you can imagine, we talked about raw data and quality control data. This is actually what the raw data looks like, surface albedo in 20-minute samples. And you get a lot of spikes, a lot of noise in the data. And there's actually good reasons for why we get this. You wouldn't expect greater than 100% albedo. You can't reflect more light than what's coming in, right? So something must be wrong. Some of these are actually snow events where you actually get snow landing on the top sensor, but the bottom one is still clear, and so it is actually picking up more light than what's coming down. And so we'll have to go through a screening process to filter out these spikes and events that obviously are not real. But you can sort of see the general downward trend as the snow is darkening and then the ice is darkening as it begins to thaw. And if you just do a simple daily average, you can pull a lot of that information right out. And so the thaw period starts, mid-May and continues downward into late June and early July. And remember, the lake is actually still frozen at this point. So we're getting about 20 to 30% reflection from the ice itself, the dark ice now. So why is that important? Well, this is what the solar energy looks like if you distribute it between the amount that's incoming and the amount that's reflected. So the actual light intensity that's measured by these Hubble light sensors is in units of luxes. And the incoming is shown here. So there's, the summer solstice that should max out somewhere in this time period here. The reflected then is this part here. And it's the gap between that determines how much is actually getting absorbed by the lake. So you notice these are beginning to diverge and diverge and diverge. And so that means that this amount of solar radiation is getting absorbed, and it's doing some sort of work on the lake. It's either thawing the ice or it's warming up the water temperatures. Well, in this time period, it's only going into thawing the ice. And that's why this albedo parameter is so important, particularly during this thaw period. So I'll highlight this period again here. That's the rapid warming period, not the rapid warming period, the rapid thawing period that shows up here. All right, so this is the rapid melt and eventual warming, and that's where all that solar radiation is going. It's going into melting the ice and warming the lake. Then what happens? Well, then all the solar radiation is going into different processes, namely evaporation and sensible heat flux. So moving on to the summer time period, again, this was the new Kalon/Gleon data buoy. It was custom built by S2 Yachts in Holland, Michigan, together with Custom Electronics in Grand Rapids. We put in multiple sensors, 2 of each essentially. We found through practice and leaving instruments in the Arctic for 6 to 9 months without visiting them that eventually something's going to fail. It's not if, but when. So we have 2 solar net radiometers and long-wave radiometers, 2 Weissela WXT 520s measuring wind speed, wind direction, air temperature, humidity, precipitation rate, and barometric pressure. There's a antenna here that wirelessly sends the data to the National Weather Service office in Barrow, about 3 miles away. And we have some webcams on top as well to measure the weather conditions and any other wave activity, other things going on in the lake. So this is what some of the data looks like. These are hourly averages of air temperature and water temperature. So the air temperature, as you can imagine, is quite variable. There's some longer-term patterns here. This is just the summer period, but it's much more variable than water temperature. It doesn't have nearly the heat capacity, and the water temperature is simply responding in a delayed sense. I fit a curve here to give you a general sense of how the air temperature behaves seasonally, and you can see the water temperature definitely lagging behind. The red and the blue are actually different depths, 2 meters in the top, basically, indicating these lakes are extremely well mixed. It's so windy up there, we rarely get stratification except when it's a sunny day with almost no wind. This is an illustration of why it's valuable to have 2 sensors sometimes, even when they both work. They'll give you slightly different answers. This is the rain rate or precipitation rate from the start of the season all the way to the end. These are individual events. And remember, these are separated by about as far apart as my 2 hands on the same buoy. And by the end of the year, you get about a 15 to 20% difference in the total rain rate. And precipitation is just one of those things that has a fair amount of spatial variability, but the sensors themselves have some uncertainty. And so it helps to at least see that you're in the same ballpark and be able to provide some assessment of the uncertainty. Bob's Pizza. Must be lunchtime already. All right, so the wind and waves, this is an example of where it came in handy because we actually did lose a sensor. One of those Vicelas, the wind sensor, just for whatever reason, stopped working in the middle of the summer. That's the flat line down here. Fortunately, we had wind speed from the other sensor, and they matched up very well during the time when there was overlap. And you know, this is why we did that. Barometric pressure sensor shows some of the variations. We're right at about sea level. And wave height, as measured by a 3-axis accelerometer on the buoy, shows a very good relationship to wind speed. And in fact, if you plot one versus the other, you can get a very nice wind-wave relationship for this lake. And it's important for these lakes because it does relate to their formation and demise processes. These, you might have seen from the map I showed earlier, they're heavily oriented in the same direction. They're all kind of elongated oval lakes. And their orientation is largely determined by the prevailing northeasterly winds and the wave activity that generates cells that eat away at the north and south end of the lakes. So we're interested in how the winds relate to the waves, and you definitely see a very strong nonlinear relationship as you would expect based on wind power. And so as you get to higher and higher wind speeds, you get much higher waves. And we're really interested in seeing what this looks like on Lake Teshepuk, which is the largest lake and easily gets waves over 3 feet. All right, so that's kind of an overview of the Kalon project. The fieldwork will continue over the next 3 summer seasons. We have a number of folks working with us this summer. And also we do field work in April. So I generally get up there when the ice comes off, which is usually around the 4th of July. So I miss all the fireworks and I'm out standing on lake ice instead. But then also in early October, which is when they freeze up. We were really interested in the timing of the ice on and ice off, because that's honestly, that's what we see changing most dramatically in that region is these ice on, ice off dates. The ice-free season has increased by about 20% over the last 20 years. All right, so back to the lower 48, and I'll be taking us back to Lake Superior as an example or a lead-in to the Global Lake Temperature Collaboration Project. And I chose Lake Superior because it is kind of one of these harbingers of climate change. It is one of the most rapidly warming lakes in the world. And again, this is the instrumentation we have out on Granite Island, just north of Marquette, to measure not only temperature, but the impacts of temperature on other processes such as lake evaporation. Another reason I'm interested in the Great Lakes, we talk about macro systems, and so I asked the question, you know, the Great Lakes, are they as macro as they get? And, you know, they're macro in the sense that they influence their own weather, and that's the interaction, the two-way coupling I was talking about before, where you can get lake effect snow occurring over these systems, or lake effect rain, or in the summertime you get an absence of clouds over the lake because the lake is so cold and the atmosphere is stable. And so the presence of the lakes themselves influence the climate that they receive. This is also kind of a joke. There is no field, I think, known as macrometeorology, but for a limnologist, this might be considered macrometeorology. Micrometeorology was the sensors I showed you on the station on Granite Island, where we're talking about, you know, small-scale variations and rapid fluctuations in humidity and wind speed. To a meteorologist, this would actually be considered mesoscale meteorology, you know, sort of an in-between scale, not the large scale, not the small scale. But to a limnologist, this is really macro meteorology. These lake effect, you know, clouds coming off the Great Lakes really indicate their far-reaching influence, not only on the lake, but in the surrounding watersheds. So thinking of lakes as sentinels, this is one of the Great Lakes Sentinels. I took this picture from our weather station, which is on a bell tower on this island looking towards the north, and this is a restored historic lighthouse on the island. And we have really good infrastructure on the island. The private landowner has really been generous about letting us use a lot of what he has on the island, such as the power infrastructure, getting to the island in the boats. There's solar panels, internet, everything. And it's helped us to develop, I guess, what I would call a network of sentinels, together with collaborators in Environment Canada, who've set up a similar station on Standard Rock Lighthouse, which is far off in offshore Lake Superior, So we can begin to look at nearshore versus offshore differences in evaporation rates, for example, driven by differences in ice cover. And now we have a number of stations set up in the other Great Lakes as well to monitor the effects of climate on the lakes. This is an aerial view of Granite Island. I like to show this along with the Native American word for the island, which is Nabaquan Island, which stands for vessel. So from the shore, it actually looks like a ship or a vessel. And this is an illustration of that. I don't know how well you can see it back there, but the winds are blowing from the west, and this is the ice cover coming from shore. And the island is cutting a path through the ice. So it actually literally does look like a vessel moving through the ice. Of course, it's the ice moving the other way. But a really neat image of that island. And this, if you look from shore, it really does look like a big oarboat, with this being the pilot house. And the kind of information we're getting from this island, it's not really a Gleon buoy, but it is a very stable platform, and we do have internet access. This was pulled off of my iPhone a year ago, showing the webcam imagery. We can pan and zoom around and look at the different weather conditions, the wave conditions. These are, some of the things you see going out on the island, really funky colors when the sun's rising and you've got fog over the lake, really windy, wavy, foggy conditions, heavy lake effect snow squalls, some ice cover forming. We've now begun to stitch these together into time-lapse video, and you can watch the ice moving by. So lots of monitoring going on. These are some big waves coming in during a storm event where we had 10 to 15 foot waves crashing into the north side of the island. Last year we had a hurricane wind gust in May out ahead of a small front. A thunderstorm was coming across the lake, and this was the only station on all of Lake Superior that picked up this remarkable wind gust. And it kind of caught the Weather Service off guard in Marquette. We've been working with them to integrate the data into their nearshore forecasting, and it's helped quite a bit. In fact, last night we had a repeat of this event, and we got a 64-mile-an-hour wind gust ahead of a squall line, and within minutes they had a warning out to mariners based on this one event, because again, it didn't, for whatever reason, it's not showing up at Standard Rock, it's not showing up at the coastal sites, and they're really starting to realize that there's a lot going out on the Great Lakes that we don't know about simply because we don't have enough observations. And with this event, 76 miles an hour, a sailboat that would have been out there at the time would have been completely swamped. So we need better warning systems, not only for the science and the evaporation and impacts on water levels, but just for the boaters and the local community and the Coast Guard. They've been looking at this information as well. So these are the two monitoring sites. Again, Granite Island, Standard Rock. This is the real-time evaporation data we get coming off the island. That's H, the sensible heat flux that I was talking about earlier. LE is the evaporation multiplied by the latent heat of vaporization. So we get that kind of data in real time. And it's changing. And it's changing partly because ice cover is changing. This is an example of a relatively high ice year on Lake Superior. And this is an example of a relatively low ice year on Lake Superior, where you generally just get the ice cover along the shoreline. So this is a time period where we would actually see a notable difference between Standard Rock and Granite Island, because one would be covered with ice cover and the other is not. This is what the overall change in ice cover looks like on Lake Superior. This was put together by a former grad student of mine, Katie Van Cleve. And what she did is she binned the total ice cover on Lake Superior into percent aerial coverage, so greater than 5%, 10%, 20%, up to 80%. So the blacks indicate really extensive ice cover during certain years. So severe winters in the late 70s, some other ones in the mid 90s. But you can generally see that those tend to start going away. And if you look at the starts and ends of these seasons, which we define as being the 5% ice coverage level, this is the decline you see through time. So roughly a 2-week per decade loss of ice duration on Lake Superior. But what she also found with this, which was quite interesting, is that you'll notice that there's quite a change in 1997-98. There was a very warm El Nino winter that year. The summer of 98 ended up being really warm. And she found that if you split the trends right during that time period, you get insignificant trends both before and afterwards. And so what we did is we ran a step change analysis throughout the entire data set, and sure enough found that this was the most significant step change. And so if you just simply calculate the means before and after that, this is really a much better representation of what's going on in the Lake Superior system than a simple linear change. All right, so there was some sort of regime shift. We think it may be related to changes in the Pacific Decadal Oscillation, which is related to ENSO, the El Nino event that happened in 97, 98. But we really don't know. And in talking with others, it's starting to sound like there was a shift in the fisheries in Lake Superior that may have been related to this shift in ice cover and therefore temperature as well. So a 34% drop in ice duration just before and after that one event. And if you look at the mean annual cycle for Lake Superior, you can imagine that this feeds back to affect temperature and evaporation. So here's a typical year, June to May, showing an increase in water temperature, decreasing as evaporation kicks in. As evaporation kicks in, it's a very strong cooling component, so the water temperatures drop off and the ice cover kicks in. As the ice cover kicks in, the evaporation rates begin to drop. So these three variables are very strongly coupled. And so as you can imagine, if you look at the July, August, September, or summer mean water temperatures for Lake Superior, you also see a large jump in 97, 98. So this was the warmest year on record on Lake Superior up until last summer. All right, so that's now been beaten. That would be over here. So that trend may start to be continuing upward again. But this was the most significant change that she found in that step change analysis. So about a 3-degree increase. The rapid warming of Lake Superior is also seen in a comparison of water and air temperatures. So if you look at the period 1948 to 99, going back quite a bit further, then the blue bars indicate the trend in water temperature. The orange bars indicate the trend in air temperature. And you find this time period here where the water is actually warming more rapidly than the air temperature. In fact, there's a period where the air temperature is cooling and the lake is actually still warming in October, November. So this is a little bit puzzling from an energy balance perspective, and I'll explain that in a moment, but it also implies that there's likely increases in evaporation during this time of the year. And in fact, that's what we saw. If you look at evaporation rates, and this is estimated from a model, we don't have evaporation data going back this far in time, but the Great Lakes Environmental Research Laboratory in Ann Arbor puts together a 1D thermodynamic model that, as a matter of fact, predicted these larger increases in evaporation during that same time of year. So a greater water-air temperature gradient. So we looked at the actual data from Standard Rock, one of our observation sites, and did in fact find that the really warm year that we had in 2010, which was another El Nino winter, so we had 2009, 2010, warm winter, low ice cover, and 2010 was a really warm summer. This is the cumulative evaporation rate for 4 different evaporation seasons starting at ice off. And if you accumulate the evaporation throughout that entire year up until the next ice off, what you find is that the other 3 years match up pretty closely by the time they get to the end of the evaporation season. But the really warm year ended up with 25 centimeters more evaporation by the time everything was said and done. And it was all because of this early start to the evaporation season. Normally you actually get condensation on Lake Superior in June and July because the water's so cold and the air is humid. Vapor pressure gradient is downward. Didn't happen in 2010. In fact, it didn't happen in 2012 last year either. We also had an early start to the evaporation season, and we can measure that with the flux data on these islands. Now you might think, well, 25 centimeters, that's that much? Is that really that big of a deal for lake levels? Well, the issue with climate change, of course, is that this might become the normal in 30 years. If every summer is like 2010, that means we're going to be losing that much more water every year. And you accumulate that through time. And of course, the lakes are going to drop unless it's compensated for by increases in precipitation. So in fact, this did lead to recent low water levels on Lake Superior. You can see that these are the average curves for Lake Superior water levels. They tend to go through a seasonal up and down every year. These are the record highs, these are the record lows, and this is the blue curve, the actual data for last year, which is 2012. And you can see that instead of continuing to rise into August and September, the lake actually started to drop earlier than it normally does. And we attribute that mostly to the increases in evaporation that started much earlier in the year. There was also the drought last year, of course, too, that led to lower precipitation and had an impact as well. So low water levels on Lake Superior, record low water levels on Lake Michigan Huron. This was just this past winter. In January, they hit record lows, And of course, this is picked up in the media quite a bit because it impacts a lot of different sectors. This is the record warmth that we saw for Lake Superior. So the blue is the average and the red is what happened in 2012. And so this actually exceeded the 1998 event as well as the 2010 event. And again, you can relate it to the early drop in lake levels. So why this rapid warming? You know, the other folks have picked up on this as well. This is a paper by Jay Austin and Steve Coleman at the Large Lakes Observatory, and they noted in a similar fashion that the water temperatures on Lake Superior are warming more rapidly than the ambient air temperatures in the watershed by about a factor of 2. So it's warming about 0.5 degree Celsius per decade over air, and the water temperature is about double that, over 1 degree Celsius per decade. And they suggested that it is in fact related to this ice albedo feedback. You get less ice in warmer winters. Less ice means less reflection. That gets back to the albedo effect I was talking about earlier in the Arctic lakes, so that you absorb more solar radiation later in the winter and especially early spring when the sun is higher on the horizon. And that leads to an early onset of stratification and then a much warmer water temperatures by the time you get to summer. So an interesting hypothesis, at least for Lake Superior, but it may not actually be the operating mechanism. And the reason I came across this and the reason I have this fellow's face on this particular slide, this is Philip Schneider. For any of you that know Philip, he was a postdoc at NASA JPL, worked with Simon Hook. And I met him at an AGU meeting in 2009, and he presented this work showing rapid warming trends for lakes in California and Nevada. And rapid warming trends that were identical to Lake Superior and were twice the rate of the air temperature. So he's seeing the same thing in these lakes in the Southwest. And he was aware of the paper by Austin and Coleman, and he said it's an interesting hypothesis, but we got one problem here for these lakes. They don't freeze. So it can't be ice, at least for these lakes. So something else is going on for these lakes. It may be different for Lake Superior, or may be some sort of common mechanism that we're just not thinking of. So maybe it's not an ice albedo feedback. Then what? And so an obvious question that comes to mind is, are these lakes somehow hypersensitive to climate change? You know, would they be warming more rapidly than the air temperature? So I thought, well, to examine this, we could possibly look at Sparkling Lake, because we have all the energy balance data for this lake. And if you look at the water temperature trends and the air temperature trends over a similar period to Lake Superior, you see, in fact, a warming of about 1.5 degrees per decade, so even warmer than Lake Superior, more rapid warming. An air temperature trend that is 1 degree per decade, so not twice as much, but 50% more warming in the lake than the air. So I thought, okay, we could look at this for Sparkling Lake. And to do this, you'd turn to the energy balance again. So just a reminder of what that looks like. And I'll just walk you through these steps here. So are they somehow hypersensitive to climate change? And just based on the energy balance, you wouldn't necessarily think they would be, because as the climate warms, you get a higher air temperature. That reduces the H term, the sensible cooling from the lake, which causes the lake to warm. That's the energy imbalance. The lake warms, you get higher water temperatures. Higher water temperatures means a greater vapor pressure gradient with the atmosphere, which leads to higher evaporation. Well, evaporation is a cooling component. So there's a negative feedback going on there. And so what that does is that higher evaporation actually limits the lake warming. So if you raise your air temperature by 1 degree Celsius, you actually get only about 0.7 degrees Celsius of lake warming because of that negative feedback from evaporation. If you just run the physically based models, that's about what you predict is 70% lake warming compared to air warming, not a factor of 2, which is what we're getting. So the exact opposite. So this evaporation feedback is negative, and in fact, if you look at 10 years of data from the paper I showed earlier for Sparkling Lake, you do see this negative feedback. So during years when you have high evaporation, which do tend to be the warmer or sunnier years, you have a reduced surface to air temperature gradient, not an increased one. All right, so it's not the water temperature gradient driving evaporation, it's the other way around. Once you get to interannual and long-term trend timescales, evaporation drives the water temperature. All right, so not likely. Then what? this was really the part of the origins of the global lake temperature collaboration. At least that was what was going on in my mind when some guy named Tim Kratz approached me at a get-together. It might have been when you were actually heading off to NSF, and you dropped this idea that you had a conversation with Pete McIntyre, also at University of Wisconsin, talking about these warm years, these anomalous years. Are we seeing these just in the Great Lakes? Or are they looking at other lakes? Is it showing up there as well? And so Tim talked to me and said, can we look at this from a physical perspective and try to understand what's going on and look at a number of lakes? So I thought about this for a moment and said, do I have time for another project? Probably not. But then I thought of a sign that I found on Apostle Island's cafe one time that says, you're either part of the solution or you're the part of the precipitate. So I was kind of excited about this issue, and I thought I really want to, kind of look into this, but I can't do it by myself. And the other thing, which is probably harder to read here, is sort of an Aldo Leopold-esque quote: if you don't climb the mountain, you can't see the view. So I thought, okay, how are we going to climb this mountain? And I remember mentioning to Tim at the time, I was like, wait a second. I know this guy Philip, who was doing some satellite-based work. They found something similar to Superior, but not the same mechanism. Maybe we should talk to Philip. So it turns out at the same time, Philip and Simon, his postdoctoral advisor, came out with a new published study that looked at these global satellite trends everywhere. So not just the southwest U.S., where they are warming rapidly, and these different colors indicate the rate of warming. But you can see that there's hotspots in the Great Lakes in northern Europe and the southwest U.S. And so Philip said, well, I don't have time. I just started a new position in Norway, but I'll talk to Simon. Simon says, great idea, I can be involved, but I probably don't have time to lead the project. So I got a hold of David Livingston in Europe, because I know he had a lot of contacts out in that region. And I said, you know what, between all of us and the Gleon network, we can probably pull this off. So we started bringing together folks through email invitations and networking, and eventually had a special session at the International Association for Great Lakes Research meeting in Duluth in 2011. And this was looking at global trends in lake temperature and associated impacts on lacustrine systems, including ecological impacts. We had about probably 15 to 20 investigators at that time, and realized that what we really needed to do was write a grant to bring together everybody in a workshop setting, an international workshop, and that eventually happened last year, June of 2012, in Lincoln, Nebraska, and we had about 40 different investigators, many of whom you probably recognize in this photo. So the outcomes of the workshop can be found online. We have a website, very simple, laketemperature.org. Talks about the origins of the GLTC project, some background on the research questions and the data sets and the list of participants, some outreach material as well. And so the fundamental question that we're looking at with this project is what are the mechanisms, patterns, mechanisms, and impacts of global lake warming and or cooling, with an emphasis on looking at both satellite and in situ measurements, because what we really recognize is that satellites and the in situ data give you two different but very valuable things. The satellites give you the global picture. They only go back to 85, so we can't get really long-term records. They only see the large lakes, so we can't probably see Lake Lacawac. But you can combine that with the in situ measurements, which in some cases go back to 1900. They are measured on small lakes. They also give you vertical temperature profiles in many cases. The satellites just give you the surface temperature or skin temperature. So what we're trying to do is essentially build a hybrid data set that's kind of the best of both worlds. And first of all, assess, are they seeing the same thing in lakes for which we have both? And what are the global patterns? So these are, and I'll just go through a few slides that show some of the preliminary results. We're still working through a lot of the detailed statistics to make sure that we're doing our due duty and due diligence and doing the rigor of the statistics. But right now, this is sort of where things stand. We have a distribution of lake surface temperature trends here measured by satellite and in situ, and I plotted them on the same histogram. And generally what you see is a few things. The vast majority of lakes are warming. There's only a few that are cooling. Most of them are not statistically significant. But interestingly, the satellite and the in situ overlap nearly identically. And these were not chosen to be lakes that are measuring both. This is just whatever we have in satellite, whatever we have in situ. The overlap is actually very little. So it kind of gives you a global picture that for the most part lakes are warming, and on an average of about 0.5 degree Celsius per decade. So what about this enhanced lake warming? What we did next was we compared this with the air temperature trends. So we have the lake temperature trends for all those different lakes and the air temperature trends, both in degrees Celsius per decade. The one-to-one line would be if they're warming at the same rate. Anything above that means the lakes are warming more rapidly than air temperature, which, as I said before, essentially violates the laws of physics unless something else is going on. We have an idea of what else is going on, but we're sort of in the process of analyzing the data to sort that out. So you notice that the majority of the lakes actually fall in that enhanced lake warming category. Very few fall in a subdued lake warming, and very few fall in the cooling category, and actually none down in this domain here. So something curious is happening with the world's lakes in terms of their warming rates. This is what the database looks like for the in situ records. I actually would have to update this as of the last couple of months because we are now up to about 90, I believe, in situ records, so it fills in some of the gaps. But as you can see, the in situ data is clustered where you expect it to be, mid-latitudes where there's a lot of lakes and a lot of people. We'd like that to be expanded. When you do include the satellites, of course, it helps quite a bit. So that's the value of including these two data sets together. We're hoping to get up to about 300 lakes by the time we publish the initial data set. So updating the trend analysis, and now this includes all the lakes, this is what it falls out to be, roughly a mean of about 0.5 degree Celsius per decade. We have one lake in New Zealand we're still trying to wrap our brain around. It's warming at 1.6 degrees Celsius per decade. Even the New Zealanders were surprised by that one, and I think they're looking back at their data set to make sure something's not wrong there, but that's Lake Tarawera. So Lake Superior is up there at the 1 degree per decade range, as are most of the Great Lakes in the southwest U.S. So the ongoing work right now, we're currently examining a variety of controlling factors, so comparing the lake temperature trends to their location, their elevation, the lake morphometry, mean max lake depth, the lake surface area, to see if there's any geographic controlling factors that determine which lakes are warming or cooling most rapidly, and also potential biological impacts. We have some lakes that have enough detailed ecological data that we can say, okay, is there a change in water clarity that's impacting the water surface temperature trends? Maybe it's not physics impacting the biology, but the biology impacting the physics. And of course, climatic drivers, not only air temperature, but cloud cover and others. In addition to the science, we have quite a bit of outreach that we've done with this project. There was an EOS meeting summary published in the AGU newspaper. We have some educational informational posters, a data paper that is being prepared as part of this project, so the data will actually be published and can be accessed by anyone. And some of you may know Lisa Buoy. She wrote a number of articles in Water Currents on National Geographic Online discussing some of the work. And she did a really nice job. So that's about it. I just want to make sure I acknowledge all the different investigators on the Kalon project as well as the GLTC project. You can go to either one of these websites to get more details on the list of participants and the project objectives. A special thanks especially to the data analysis subgroup with the GLTC project. Derek Gray, Stephanie Hampton, Catherine Riley, Jordan Reed, and Sapna Sharma, because they've been doing a lot of the grunt work and making sure we get all the data processed in a systematic way. And then, of course, a number of funding agencies, NSF, NASA, and the University of Nebraska-Lincoln, that contributed significantly to the funding of the workshop. So that's all I have, and I'd be happy to take any questions. Thanks.